Looks like I'm live now. Or it doesn't look like, I'm not sure. Okay, looks like I'm live now. Hello, everybody. Um, it's kind of weird to say everybody when I know there are no audience in the live stream, but awesome. I confirm that I'm live now. Okay, let's give a quick introduction for the one who is watching this for the first time. Uh, so I'm a senior software engineer. Uh, have been in the industry for more than a decade and uh, have done this interview preparation a couple of times before. I stayed in my first company for a long time. I worked there for close to 7 years, and then I switched a couple of times. Um, yeah, and how is it different to this time? So since I did prepare a couple of times, and I prepared when I was out of college, the same things. Uh, I do not have much of motivation to do the same thing again because this is not adding a lot to my day-to-day skills. Um, so and I was mentoring multiple people on LinkedIn. Whoever contacts me or reaches out to me, asking questions about how to navigate the job switch scenarios or how to navigate in this market and how to prepare and all. Um, so I thought I can do the same thing at a bigger scale here. So uh, I'm open to support somebody's preparation if I know that they are really focused and if they are putting in effort. I can spend my time to converse one on one and advise or um, lend my thoughts and valuable inputs, I would assume, based on my experience and past experience and based on what I see in the market, how we were conducting the interviews in the companies that I worked for. I worked in one of the FANG companies, the one which I stayed for a long time, and then I switched to mid-sized companies. I wouldn't say those as like the startups, but those were like close to 3,000 employee and in that scale. So those were like and 10-year-old companies. So those were like mid-sized companies when I joined. So yeah, that's about me. So about my preparation style. So uh, no matter how many times I prepare, always it takes some fluency. Like for example, I had not coded in Java for past 3 years in a professional capacity. I used to code in Java in my first job and also when I was in college. But but not recently. So I need my muscle memory back. I know the data structures the best in Java because I have done it multiple times. So I get back to Java whenever I need to prepare for this data structure and algorithm style interviews. Mm, that's the only reason. I feel Python is pretty straightforward as well. Like when I'm conducting the interviews, I have seen a lot of people using Python. Python is the most popular, I guess, for these kind of interviews. And as an interviewer also, it's kind of easy for me to see what they are typing and how they are coding, like without having to spend a lot of effort. It's kind of intuitive to understand that code. So I would recommend that as well if someone hasn't decided on a programming language to code. Um, yeah, I think that and everybody has their reasons and has their reasons to start using a programming language. Maybe it's the need for their first job, or maybe uh, that's what they liked. Like, for example, few people might start working in their first job on a Django framework, which is pretty quite popular for prototyping and things like that. And few people who have started with big forms might still use or start with Java, and some people might start at low level coding stuff with C or C++. So I but yeah, anything is fine, like as long as we are comfortable translating our thought process into a workable code. I think that should be good. Okay, coming to this this term's preparation. So as I said, I was getting bored to do the same repetitive things again. But still, I'm not like, I wouldn't say like I'm 100% ready to face the interviews tomorrow. So I need to gain that fluency. That's why I'm doing this. Usually, my process is like I start with the basics. Uh, the thinking behind this, like I can start with directly from like LeetCode, like most frequently asked problems, company wise and all. So that would be like a good preparation as well. But I feel dumb when I go to solve those every time. Um, I feel that okay, I'm not capable of solving those as of yet. I need some practice, some muscle memory, and some basics. So I just glance through each data structure. Um, Even though I know I understand it, like I like solving these as well, and looking into and implementing these data structures. Like I keep improving with my experience. I have kept improving with my experience as well. The way I approach and implement these data structures or think about their implementation as well. So that's a good thing. Like, and I enjoy that exercise. And also that I feel that somehow if I start with the actual lead code problems or some programming problems, it's like I gain the ability to solve that particular problem. But if I start from the basics, that gives me the ability to solve any similar problem or anything related. So in the interview, like if I don't want to depend on luck alone. Um, so if I'm lucky, I might get the problem which I have already seen. But more often than not, like there is a good probability that they will ask their own question, which is not seen before, or they would try their best to do that. In those cases, these basics are very handy. Like if we know the basics well, that means we are able to cover any tough problems or any related content as well. So yeah, that's kind of that's the reason I go from the basics and try to implement the data structure, underlying data structure, and understand their operations and different scenarios when they should be used and things like that. Once that is clear and out of the way, algorithms. Coming to algorithms, get uh, I get nervous a little because for me algorithms are not as intuitive as the data structure. Data structure, it's like it feels like common sense. Um, if we think of like linked list or arrays, we know when it has to be used. For example, arrays has to be used when there is when we know the indexing, and when we know that okay, when we know that we have to fetch something from a particular index or search if that exists in a particular index. And insertion is little difficult in arrays, insertion in a particular index, because if we want to insert something in between, then that means we have to move all the elements after that, because arrays are stored in contiguous memory locations, whereas in linked list we are storing it as link. So we will kind of disconnect a link in between and then connect and form another link if we need to insert in between. So we will see. We will choose and pick according to the scenarios. Same way, queues and stacks. Yesterday only we discussed about queues and stacks indirectly while implementing DFS and BFS in depth first search. Since we are going deeper into every node that we meet, we are using stack. So last in first out. Stack is last in first out, and whichever the node that we insert last, we will pick that and then we will keep going. But that's why kind of we keep going deeper into the depth. That's what happens in depth first search. But in BFS, which is breadth first search, what we do is we are using queue. So from the source node, we will add all of its neighbor into the to be visited queue. So in that queue, okay, we have added all that into the queue. In queue, what happens? In queue, it's like queue is uh, queue helps us follow the ordering. So whoever is added first into the queue, first in, first out, they will come out first. So like we have added those three, like let's say the root node has three neighbors. we have added those three nodes or the neighbors into the queue. So we will try to process them first, and then while processing we will add their respective neighbors into the same queue. So they will come next after this level is complete, or after the immediate next nodes to the source is complete. That's how, like, we will go level by level. um, yeah, I think that's what we looked into it. So it's good that we revised DFS and BFS as well. So we can go and revise Dijkstra's as well. In the same way, the difference between breadth first search and Dijkstra's is, in breadth first search, we were solving the um, what is that? Uh, Closest path, or mm, shortest path shortest path algorithm to any node from source to destination. We were using breadth first search algorithm for that. But if the graph has weighted edges, or weighted like distance between two edges, that means we cannot solve it using just breadth first search. We have to use Dijkstra's algorithm when the edges are weighted. So in Dijkstra's algorithm, how it works is, we start from a source, and then we see, like, and then we enter it as, like, we will maintain the already visited, and we will maintain already visited arrays where, um, let me say, for already like weighted nodes. And also another condition I forgot to mention, the weights should be always positive. So if there are negative weights, Dijkstra's algorithm wouldn't work. In order to tackle the negative weights, we need to use Bellman-Ford algorithm. So that is we might look into it today, or maybe not in the near future. Let's see how the time permits. So in Dijkstra's, what we do is, basically, I would say here. Let's go here, and I'll start the call as well. I mentioned the call details in the if someone wants to ask me a question, and if they are not able to conveniently do that, that's why I added call information. Yeah, let's see if someone wants to join. I'll keep it open. Okay, let's come back to Dijkstra's. So in Dijkstra's algorithm, so we had this thing. So from node 0 is given as source, and then from node 0, like, we have immediately two neighbors, and from node 0, the distance to node 0 itself is, we know that it is 0. So we can add that as distance from 0 to 0 is 0. And then from 0 to, like, we will look at the shortest node next to it. So we have two nodes from node 0 which are shortest. So we can move to 1, which has the distance of 4. So once we move to 1, so next one is, we need to see from 0, like, we are concerned about the shortest path from the source, not from 1, or not from the next nodes or anything. From the source, the shortest path was this one, which is 4. And then from 1 to 2, we will have to add. So this first, the distance was 4, and to 2 it is 4 plus 8, it will become 12 to 2. Whereas to 7, the distance is 8, so we will go to 8. So now we have the comparison points. Either we have to compare 2 or the neighbors of 7, which is 8 and 6 node. So what's the distance for those? To 2, we already calculated 8 plus 4, 12 is the shortest distance, as we know from the traversal till now. And from 0 to 7, it is 8. And from 7 to 6, it is 1. 8 plus 1, 9. So from 7 to 8, it is 7. So 8 plus 7, 15. To 8, it is 15. To 6, it is 9. To 2, it is 12. So 9 is the shortest. So we will go to 6 now. So we are entering 0, 1, 7, 6 to the distance map that we have kept. So those are the finalized distances. So nothing is shorter than these things. Like, so let's say there is another path to 6 somehow from wherever, it has to go through either 2 or it has to go through either after 8 somehow, right? Like, because we have already exhausted all the paths before. So it had the 8 plus 1 9 should be the shortest path to 6. So we have finalized the shortest path to 0, 1, 7 and 6. So next one after this one, we have a path to 5, or we can consider to 8, or we can consider to 2. So for to 2 it continues to be as 12, to 8 it is 8 plus 7 15, and to 5 it is 8 plus 1 9 plus 2 11. So this is the shortest. So now 0 1 7 6 5 are confirmed, and now we have in contention uh, either 4 or 3 or 2. So 2 from here, I mean, or we can consider from here also. So here if we see 8 plus 1 9 plus 2 11 plus 10, 11 plus 10 21, here 11 plus 14 25, 11 plus 4 15 to this 2, but here it is uh, 4 plus 8 12 to this node, and here this is, I think we didn't navigate to this 15, I guess. So this 15 was also there from 7 to 8. So this one is 4 plus 8 12. So this is the shortest one. We came to 12 here, I mean 2 here with so it is like we finalized for 0, we finalized for 1, and we finalized for 7, and we finalized for 6, we finalized for 5, and we finalized for 2. For 2 it is coming from this path, and after 2, like we can check the immediate next one. So this was 15 here, 15 plus 2, sorry, 12 here, 12 plus 2 14, and 12 plus 4 16 here. So within that path we will check, and to 7 plus 8, 8 plus 7, this is also 15. So this is the 14, at least the shortest one that we are seeing now. And to 8 from 6 also, it was much more than that. It was 15. So we will consider this as the shortest path now. So we will update this as 14 now. So we had not finalized 8 until now. So 0, 1, 7, 6, 5, and then 2, and then now we are updating it as 8 as the next one. So now since this one is finalized, so now the remaining nodes are 3 and 4. So we know that 4 is nearer, or maybe from 12 this becomes 19. So 3 is nearer from this distance. So we can enter this one, and then yeah, 3 is finalized, and then this one also we will find the shortest path either from this side or from this side, and then we will update it. So that's the logic. And then let's look into the code. I wrote a code like which is little bit unconventional probably, but I checked that. I verified it, I guess. So yeah, so this is like I'm defining my own node with weight, because I had defined a graph here like for DFS and BFS. We saw executing this code yesterday. Here the node that I have defined is array list of node only as neighbors and the data. But in the other graph, maybe I can manage all these scenarios in the other graph as well by managing the weight as consistent as like a unit weight, like 1 or 0 as the weight, which is equal between each node. So I can merge it later, but yeah, that is another topic. But coming back to the here, I have a node with weight defined. So in that there is a int data. Data is one thing, and then a list of edges I have maintained, neighbors. And what does the edge consist of? I have seen, so edge is consisting of a node and the weight for that node. So what I meant to say is like this is like saying, like if I have maintained a list of neighbors, means in that list of neighbors I'm defining it as an edge, list of edge. So an edge consists of both the information, basically to which node it is going and what's the distance to that node. So I have that list here defined within the node, and yeah, the usual constructor, and this is toString to just make it easier for to print and show it in the in here. I should remove all these toString methods later, and then I have defined pair. I think if I have to push it to GitHub or later, I'll just make these as separate classes, all this node weight, and try to combine this graph or scenario also with this one. I like making it generic rather than trying to create thousands of classes. So that makes it easier to understand as well, having a consistent pattern for each data structure. So here in the um, graph with weight, I have been maintaining a nodes map which maps from an integer to the actual node. So integer is the value and the nodes is the list of nodes. So that is there. So let me take a second. I'm hearing some disturbance here. I'll get back to it. Okay, I realized there was no audio. Man, I explained so much. I thought I was the last sentence I was telling that I felt good today with my explanation and whatever we did until now. We revised DFS, BFS, and Dijkstra's, and I showed my implementation for Dijkstra's algorithm. At least the screen would be there, even if there's no audio. The code that I shared, the entire code, and how I have represented the graph, and how I have represented the graph without weight, and how I have represented the graph with weight. So that is all given. uh, yeah, so that is all clear, I guess. And how the Dijkstra's algorithms work. So we just keep going to the immediate uh, best route or immediate shortest path, next shortest path, and then next shortest node, and then we keep doing the same thing. And since there is no negative weights, so there's no way that okay, the weight of the next available shortest node would be less than what it is currently after we traverse from the other possible route, because it is the shortest now. It cannot get any better than this if we go via the other route which is available, because other route is already higher weight or higher distance from here. So it would, even if we go another path, it would be higher distance only. So we keep seeing with every node, okay, what's the next immediate closest node. And the code is pretty good. You should watch the video that I've shared. I'll see if I can go over it again. Um, it's a good implementation. I think I liked it. I have defined the graph representation as an edge and list of edges and the data, and I was able to implement Dicestra's algorithm, and I was able to verify it with the problem that's given in Geeks for Geeks. The same thing. It was working fine. And shout out to Rajesh. So he mentioned that okay, he was not able to listen to audio. That's when I realized. Thank you. I had paused it and forgotten to unpause. Uh, Sorry, I had muted it and forgotten to unmute it once I came back. Man, that was such a... Okay, whatever. So now it's gone. It's out of the way. I don't know if there were any other viewers in the meantime. I hope there weren't any. If someone joins now, I'm happy to go back to that and explain it in detail. Otherwise, I'll just move on and go through the problems here. So let's take a couple of seconds break, and not couple of seconds, couple of minutes break. I'll just drink some water and then come back. Hello, hello. I'm back. Hey, Madhu. I had muted it on purpose for a break now, but now I think it should be audible. Um, so let's get back. So we were done with the Dijkstra's algorithm. So let's go back to our usual lead code problems here. Okay. I think I had few of the depth of search solved already. So let's not go back to that unless someone has a questions. I think I explained it today again. Like overview of the depth first search algorithm, ACDBE, ACDBE. So if we used something like breadth first search algorithm, then we would have come like ACE. So uh, its immediate neighbors first, and then from C to D, and then from E to its neighbor B. Like it should have been like ACEDB, something like that. But in depth first search, if we go to from A to C, we'll go to its neighbor and its neighbor and its neighbor. So that's how we traverse. So that is what is explained here. And traversing all the vertices, depth first search algorithm. So traversing all the vertices, it takes O of B plus E, where B is the number of vertices and E is the number of edges from those vertices. We represent the number of vertices and we represent the number of edges. We need to check every vertex and traverse through every edge in the graph. That's why the time complexity. Um, yeah, even after traversing that edge, if the node is already visited, then we do no ops basically. And then space complexity is O of B. We just store whether all the vertex is visited or not. That's what's mentioned there. Yeah, and traversing all paths between the two vertices. So let's see, in this one, traversing all paths between two vertices means okay, this was a bit tough because there is a lot of probability involved. So that's why explaining the time complexity and space complexity was a little tough in this one. So here, I need to play the video, but I don't want to because this is like a premium content from LeetCode and I need to respect that. At least I'm showing and I'm using their curriculum, but I don't want to use their content as well. So basically, I think this says the number of arrangements. Basically, uh, all the possible paths means we know backtracking, right? We follow the same thing, same approach. We'll explain how to find all the paths between two vertices using the depth first search approach. Hmm. Hmm. In a complete graph, there will be v minus 1 unique paths of length, one that starts at the source vertex. Uh, one of those paths will go to the target and end. Each of those remaining paths will have p minus 2 unique paths. So what it is given is what they have given here is in a complete graph. What do you mean by complete graph? Complete graph means there is an edge from each node to every other node in a graph. That is called a complete graph. So in a complete graph, so there is a unique path from there is v minus 1 unique paths uh, of length 1 that starts from source vertex. So from source vertex, we have like if there are v nodes, from one node to go to any other node, there is like v minus 1 different paths. Once we pick one of the node, then it is like we won't go to the original node or it's wherever we traveled from, but there are v minus 2 different paths remaining. In the same way, after we go from there, we have v minus 3 different paths because two are already visited. So in the same way, we have that uh, v minus 1 factorial paths, total paths basically. Remember that one path reaches the target vertex. So by the time we reach the target, there can be like v minus 1 factorial total paths possible. And then yeah, okay, that's what is here. Time complexity is O of b minus 1 factorial. The above example is an undirected graph. The worst case scenario when trying to find all the paths in a complete graph. A complete graph is a graph where every vertex, okay, so that is given. what is this one? Number of arrangements. Yeah. Okay, let's not get into so much of math. So it's given like how many paths can be possible between different node. If it's 0, okay, 1, 1, 0. Number of derangements, number of arrangements. Okay, it grows exponentially. And space complexity. How the space complexity is O of Q, the space used by the stack, which will contain V minus 1 paths after adding first V minus 1 paths to the stack. Paths after adding first V minus 1 paths to the stack. Okay, V minus 1 plus V minus 2 paths after popping one path and adding second set of paths. Basically, we have V minus 1 paths already maintained in our queue, and then we pop one of those, and then we will be adding V minus 2 paths from that node. Yeah, so and then and so on. It keeps going, and then V minus 3 paths from that node. So it comes to V into V minus 1, 1 by 2, V into V minus 1 by 2, the sum of this one, plus one path will will be the most in the stack. So in the stack, that many paths we need to maintain. That is O of B square that would have come to. And each path added to the stack will take O of B space. So each path can consist of, like, from a source node to the destination node, it might consist of traversing through each of the node. So in the worst case, each path might contain O of B nodes or B nodes. So that's why it is kind of O of B space. So O of B square here, V into V minus 1 by 2, and O of B space that each path can contain. So that would make it O of V cube. That's a bit of heavy math. Let's not bore you guys with that, at least so early. If someone has any questions, feel free to drop in a message. I'm happy to discuss it in the later live streams as well. And then find if the paths exist in the graph. So, okay, it is not coded also, I guess. So what's the question? There is a, why is it marked as done? Maybe not by me. Okay, there is a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1 inclusive. The edges in the graph are represented as a 2D integer array edges. Okay, where each edges of I is equal to, okay, got it. Every vertex pair is connected to at most one edge, and no vertex has an edge to itself. Okay, every edge is connected, basically. That's what they have been saying. Connected to, oh no, connected to at most one edge. The vertex pair is connected by at most one edge, and no vertex has an edge to itself. You want to determine if there is a valid path that exists from vertex source to destination. Okay, so you can see this graph, all the vertices are connected, so there would be a path from source to destination. In this path, it is disjointed. I mean, if the node exists, it is disjointed. From 0, there is no valid path to 5, or from 3, there is no valid path to 2. So yeah, so that's the graph defined. What we need to determine here, int edges. What did they say? Edges of I is equal to ui and vi denotes bidirectional edge from vertex u of I and v of I. Okay, got it. So this is a bit of weird representation because this uh, um, basically the index of this array, this is a list of list. The index of the list is the, like, now it is saying from 0, 0th index. No, I think it is from 0 to 1 there is an edge, from 1 to 2 there is an edge, and from 2 to 0 there is another edge. 0 to 1 there is an edge, 1 to 2 there is an edge, and 2 to 0 there is an edge. Okay, that's what they are saying. Edges of u of I, ui and vi denotes bidirectional edge between ui and vi. That's it. Okay, don't overthink. There are two paths from vertex 0 to vertex 2. We can come from 0 1 2 and 0 2 both. So that's why they are saying to source is 0 and destination is 2. Yeah, there are two paths and we need to just mention it as output is equal to true. And here they are saying they have 6 nodes. Out of that they have given the existing edges. Between 0 and 1 and between 0 and 2 there are edges. Between 3 and 5, 5 and 4, and 3 and 4 there is an edge. I said 3 and 4 instead of 4 and 3 because it's bidirectional. And source is given as 0, destination is given as 5 from source, destination. With this representation, it's easy to mention that, okay, there's no valid path here. But when there is a representation of the graph with hundreds and millions of nodes and there is interconnected edges, it's not easy to have that information. So we need to have a traversal and see if we reach that destination node. If we cannot reach that node while traversing, yeah, then we can mark it as there's no valid path. So how should we approach it? First thing is this representation of the edges. We can convert this graph to like an adjacency list or something like that. Let's see. How do I represent an adjacency list? I represent it by okay, map of integer to list of integers, or we can just call it as graph. Okay, if you guys get bored, if you're watching it later, and if you get bored, just watch it in 1.5 or 1. Or 2x speed, whatever I code here. So I'll be thinking, I'm coding in real time, so it will take some time. I'll have a timer, not to bore you guys. Okay, that's 25. So if I cannot finish it by 10 minutes remaining, so let me see the solution. Okay, graph, and then graph dot add. Okay, so now they have given the edge definition. I need to add those edges for int edges. Okay, I'm iterating through each of those edge, and then I need to add those edges definition in this graph dot put edge of 0 comma edge of 1. I hope you understood what I'm doing here. I'm just adding that. Okay, to the 0th edge I'm adding the first edge. Okay, I cannot add it straightforward because it's a list of integer or the list of nodes. So that means what I should do is graph dot put graph dot get okay, I just need to add to that that particular thing. So here let's say list of integer get or default. What will do edge of Okay, graph.get our default, this one array list. Okay, so I'm just seeing if there was an edge for 0. If there was an edge for 0, then I'm adding it. Otherwise, I'll I mean, if there is a list of neighbors for 0, I'm just taking that already existing. If there was no list for the edge 0, then I'm just creating a new array list, and that is the value here. And then I'm adding that list to this one, and then I will just append it to the graph again, graph.put, in case if it was not existing. No, I just appended it. I think that should work. I don't have to put it to the graph again because I have created a default here, and then only I'm taking it here. Okay, so now I should do the same thing for the other side as well. List 2 for 1 for edge 1, and then I'll add the edge of 0 here. Okay, now it should have simulated and given me all the output, all the graph components here. After that, what I need to do, since this is a DFS approach we are following, so I need to traverse basically. And what I'm doing, I'm searching if there is basically, it's like if there is a path between source and destination, means I'm just searching if the destination exists in that graph, basically, like in the graph while traversing. So in order to do that, I need to send the graph, and I need a visited as well. I think that's it for now. Okay, so yeah, for that visited, let's maintain set of integer called visited. Private, and this should be boolean. What's the time remaining? So if one has to crack at least meta style interviews, then you need to be quick enough to solve a question in 15 minutes. Maybe this little bit complicated than this one, I guess. So now we already consumed 6 minutes. Let's go. Just keeping that in mind. Okay, copy it wherever you can save time. Even, I mean, not just here, in the interview as well. Okay, now what we need to do, first thing is if okay, and also we need to send the source and destination. That's the key thing, right? This is visited. I just copied the type for some weird reason. I need the parameter value as well. Okay, int current, let's mark it as, and int destination. Okay, if current is equal to destination, then what should we do? Then just return true if current visited dot that contains current already, that means we have already visited it, then that means return false, or else what should we do? Or else just go over its neighbors and execute TFS for all of them, basically. For each neighbor, basically. Why am I using basically so much? Each neighbor means What is it? Node. So node is an integer here. Neighbor. Graph.get of current for the current value. Okay, I'm going through each of those neighbors, and let's see. Once I go through each of those neighbors, what should I do? Is there anybody in the stream? Okay, once I go through each of those neighbors, take your breathe, calm down, and okay, now do it. If DFS search of neighbor. Now, after the current, I'll go through the neighbor, comma, visited, sorry, should be graph, comma, visited, comma, neighbor, and then destination. And one thing we missed here, if that returns true, then return true. Otherwise, keep continuing. That's it. And if none of them returns true, then don't forget to return false. It should work. And here also, I should mark it as visited. So once those two are not satisfied, visited dot add current, so that we know that the current is already visited. And also this visited, let's check that before the first statement, because why to check if it's the current node if we know that if it is the visited, if it is already visited node, then we don't have to do anything. So no ops in that case. Okay, we might have mistakes, but let's execute it. What happened? Compilation error. DFS search. DFS search. Okay, I haven't passed the later two arguments that we defined. So yeah, runtime error now. Cannot invoke iterator because the return value of get object, map of get object is null. Why is it null? This is weird. Graph.get of current. So here map of graph.get means I have defined it as list of integer. $25 graph.get. Okay, valid path. Is it because what if there is no edges into that source or something? Okay, what's the input here? Let's see. Your input 3 is this one, 0 2. 3 is 3 in pointers, and there's an edge from 0 to 1, 1 to 2, 2 to 0. 0 to 1, 1 to 2, and 2 to 0. And then we are checking whether there is a path from 0 to 2. 0 to 2. Okay. So in this case, it should easily return true. Okay. I've added the graph, so that should be clear. Let's print the graph here and see. Can we print the graph? Oh, this might not be adding it to the graph totally. It's just the default value. It's just returning the default value as new array list. So, okay. Graph dot put. Correct. So, okay. Now it looks like it's working for this test case at least. And if we submit it, still judging. It says it's wrong answer. Done. Input is done. I wonder from zero why we have this, all this. Zero so many times. Okay, here it is mentioned as list1 dot add, list2 dot add. Okay, it's accepted now. Since the print statement was there, it was not working for the very large input. Okay, so the main culprit was this one. I should know the syntax. There might be a better syntax than making it 3 lines here. So I'm kind of get put or default. Is there anything like that? Graph dot. Okay, it doesn't auto suggest. Let's see the solution. I'll not show the solution here, but let's go there and see. Until then, you can see me. The next best thing. We are a bidirectional graph. Okay. Valid path. How many? There are 2 in the stream now. Nice. Who is it? Can you text whoever is in the stream? So from the looks of it, compute if absent is the one. I can use the compute if absent method there. Okay, yeah, that's a good learning. So how do we go about it? Let's go back there. There you go. Graph dot compute if absent. And then what's the value? Edge of 0. If there is no value for edge of 0, then it's a function which creates new array list and then performs an add operation of edge of 1 on that. Okay, and I'll do the same for the other way around as well, for edge 1 as well, by adding edge 0. Let's comment this one out and then let's run the code. Did you do anything? Yeah, I think run status is finished. Yeah, and submit it again. It's accepted. This looks much cleaner now. We can remove this commented code and yeah, graph.compute is if absent, not put put or default. Okay, let's move on to the next one. Find if paths exists in graph. If path exists in graph, so it should be the similar thing, I guess. O of b plus e, O of b plus e space complexity as well. So the next thing is all paths from source to target. This is tedious. Not difficult, but it looks tedious. There are so many different. Okay, this is a different representation here. Maybe from 0th node, there is a edge to 431. From 0th node, edge to 431. And from first node, there is an edge to 324. From first node, there's an edge to 32. That's it, 32. Oh, 4. Okay, it's coming all coming from around the head here. And then from second node, only 3. From second node, there's only 3. From third node to only 4. From fourth node, there's no outgoing edges here. Got it. And then what we need to do? We need to write all the paths basically. Okay. Let's accept this challenge and go ahead. Did we do this within time? Definitely no, I guess we went over time. Let's reset it again. No long break today. Stay focused. Yeah, let's see how much time we take. All paths, list of list. So I usually do this when the output format is given here. All paths, new array list. Okay. Now let's get the graph defined as a adjacency list again, I guess. Yeah, from 0. Yeah, let's do that. That is also kind of adjacency representation, but I feel much more comfortable in a hash map. We can reconsider it later if the array list works well. Integer to list of integer. And it should not take a lot of time. Make it fast. Int neighbor and then int of okay, it's better this way. Looping with the index, since we know that it's marking based on the index. Name it as graph map just to avoid confusion there. Graph of I. Does this work? Okay, so this one is given. So once that is done, so I need to traverse DFS traversal basically. I'll just traverse and see. And 0 to 4, 0 to 4, 0 to. Why is there's nothing from 0 to 3 in the output here? Zero, 3, 4. Okay, given an directed acyclic graph n nodes labeled from 0 to n minus 1, find all the possible paths from 0 to n minus 1. Okay, not just all the possible paths, all the possible paths from 0 to n minus 1. So it is like current then 0 and n minus 1, graph length minus 1, graph length minus 1, and then what else is needed? Current path we need, and how to represent the path. Okay, it's just a list. Current path can be a list, so I would say that as new array list. Yeah, let's see the remaining data. Private and this should return nothing. It should just append to the output. And output also. Yeah, it's another way is just make this as like class level variables and append it there. That's another way of doing things like this. And even for this one, I guess, nah, let's not overdo it. So we can just avoid this parameter and then just, yeah, but I don't like returning that instance variables here. Yeah, but it will reduce the number of parameters that we are passing, so that's the trade-off. And then let's create a then we don't need this, and also this graph map also we can get rid of, so that we don't have to pass it as a parameter. Okay, so the terminal condition, let's think about that first. Let's think about that first here. So here, destination, current path, like whatever is traversed until now. Here also int current, let's make it as int current. Okay, so now if current is equal to destination, then what should we do? If current is equal to destination, then let's just append it and return. Then current path, which is a array list, just a list of integer dot add current, and then append it to the all paths, paths dot add new array list of, I'll say why I'm creating a copy of it instead of just adding it, because I'm seeing it as like a backtracking algorithm. Maybe I need to remove that path as well. So for example, what I mean to say is I'm traversing from 0. From 0 there are 3 neighbors, so I'm going to 1, and then from 1 to, there are 3 possible paths again, so I'm 1 to 4. So okay, I reached the destination. I have to recoil to 1 and then explore the other paths as well. So if I just append that particular array itself which held this path, then once I go back here, I will be removing the 4, which is current node. I don't want and then I need to append it to 2 and then 3 and then 4, and then from 1, 3 and 4. So now if I remove it, it would be gone if I store the same copy in the output. That's why I'm creating a copy of it and then appending it to the output. So that's the reason. That's the justification. So okay, I added it. So after that, okay, that is if I reach the destination. If I don't reach the destination, then what should I do? Then for int neighbor graph map dot get current. So I need to see all the current neighbors, and then to the path I should add current path dot add current. So I should do it irrespective of both the steps. So I think I can just pull it out, I guess. And I don't have to write it twice. So added this one, and then terminal statement came, and then I've come here. I need a visited also, I guess. No, I don't need a visited because it's a directed graph, directed acyclic graph. So there's no cycle, so I don't have to worry about it. So there's no visited needed. So here, let's traverse now. DFS traversal, DFS traverse, and then current would become neighbor here. Neighbor is the current one, and then destination would remain the same thing, remain as it is, and then I need to add the current path also. Yeah, and then once that traversal is done, what I will do, I'll do current path dot remove of neighbor, so that in the when I go to the next neighbor, so that would be removed, and that would be the next neighbor would be appended to this current path. Yeah, that's how it should be. And then once all the paths are traversed, it is returned. Okay, so what am I doing here? Graph map dot put all. Okay. Compute is if absent, right? Yeah, I can do that. Compute if absent for I, create a new array list, and then dot add, or is there add all? Let's see. Okay, I need to mention type here since there's no declaration. Okay. This is a function, not actually. Is there anything like that? Okay. It might be some syntactical sugar there which is needed. Let me do this thing. Okay. Okay. Oh man, convert. Arrays dot as list. Let me know if someone knows a better way to convert it. Here nobody has made it as like that map format one, I guess. Okay, I wish there was an easier way. Rather than converting all this. What if I just maintain it here? Okay, it works here. Could work here. And it should work. Graph map output. Okay, neighbor means whichever is added last basically. So I can just remove that one. $25. Fine. It took more time than it's needed. Let's take a short break. Okay, let's hit the road for a few more today. Okay, let's see. I see that nobody new has joined. There's one viewer. The silent watcher. Okay, let's go now. I'll have to, I have unmuted already. And the last one worked like a charm, so no complaints there. Yeah, let's go back. So we are done with this one. All paths from source to target. Okay. Here, all paths from source to target DFS. Again, we have something here. Graph is equal to null or graph.length is equal to 0. Return path as it is. Otherwise, run DFS and then return that path. How am I running DFS path that add node to the path I'm adding the current node? If the node is equal to graph.length minus 1 path start add. Okay, if the node is equal to, okay, if the current node is basically the destination node, I'm not marking that as destination and passing it as a parameter here as I did now. So yeah, I'm just checking the length of the graph, and if it is equal, then I'm just adding the path to the final output, adding the current path to the final output and returning it here. And then next nodes, I'm creating the next nodes. Next nodes is basically nothing but the current graph. I don't know why I created separate variable for this one. Usually I don't do that. Maybe it's not me who has written this code. It could be, yeah, somebody else using the account. Let's do this. Yeah, this way it's better. Okay, and I'm just running DFS and removing the current node from the path so that I can backtrack and repeat the same thing. Time complexity is O of v into v. I think we looked into this one. O of 2 power v is like with every node for backtracking, we will have like two different paths to take, and then the path that we store, no, the path that we traverse is v. Okay, let's see. For a directed acyclic graph with v vertices, there could be at most 2 power v minus 1 possible paths to go from the starting vertex to the target vertex. We know that we need O of v time to build each such path. Okay, 2 power v into v, that's why. Therefore, a loose upper bound of time complexity. Yeah. Since we have overlap between paths, the actual time spent on the traversal will be lower to some extent. We could have used dynamic programming also, I guess, like from certain level. Yeah, but it's a completely different approach. From the back, we have to keep returning the path. Like basically, I need to know that, okay, from if there is a graph from the destination, we need to like destination to the previous node, what's the path? If we have come to that node and asking for the rest of the path, we should be able to just append it and return rather than recompute it. I mean, if there are multiple paths also. The recursion depth can be more than v, and we need O of v space to store all the previously visited vertices, which while recursively traversing. Got it. So this is clear. Let's move on to the next one, which is cloning a graph. So what is it? What are they doing here? Let's see. Who is in the call now? I see some viewers. If you're still there, please drop a comment so that I know who is in. Yeah, let's see. Given a reference of a node connected undirected graph, return a deep copy of the graph. Got it. Each node in the graph contains value int and list, okay, of its neighbors. So the node is in this format. We need to create a deep copy. So this is always kind of a tedious problem. In order to create a deep copy, we cannot use any references and use as it is. We need to keep following, iterating and creating with them. For simplicity, each node's value is the same as the node's index. Okay, node's index is, I mean, 0th node, I mean, value of this node is 1, value of this node is 2, like that. And adjacency list is a collection of unordered lists used to represent, okay. Yeah. So here, how do we empty graph? It does not have any nodes here. Adjacency list, okay. Got it. There are 4 nodes in the graph. Okay. So they have given a source node, and then we have the given node will always be the first node value 1. You must return the copy of the given node as a reference to the clone graph. Got it. So how do we traverse? That's the question, right? I mean, we can do DFS traversal, but with traversal, we need to keep copying. That's the challenging part. So here, let's create a copied root is equal to new node of node.val and then return copied root. That's the node we need to return at the end. And in between, we need to do this, all this DFS traversal for sure. In order to do that, we will be sending the node, okay, node and maybe visited. Yeah, in order to do the DFS traversal, we need visited. So set of let's do one thing. Rather than keeping the visited, let's do a map of current node, which is current node, to another node, which is a copied node. Okay. To copy copies map, new hash map. Return nothing. Reverse traversal, and then yeah, so here what do we do? So basically I have created a node and this one, and then we are traversing from that particular node, and copies map or copy map. Let's make it as copy map instead. So here, in order, while traversing, have a node current, and then set of, I don't have a set for visited. So I have this. I think I can do this. I can create it as an instance variable like this. So we don't need this anymore. And then we're passing that. And we don't need that. We don't have to pass it now. Okay. It's yeah. Okay. So now after this one, if copy map dot contains current node, then don't do anything, just return, because that means it is visited. If not, then yeah. So yeah, if that not contains, I forgot to put the timer, I guess, or was it on? No. So DFS traversal here, copy map dot contains current, then return. If that doesn't contain current, then what I need to do? So if that's the case, I need to check the neighbors. If the neighbors are null, then I can return. Okay, then copied current. Okay, let's not add this one here. Create this one here for now. Let's see that how it goes. Now we need to, so then we cannot use it as visited, I guess, because we need to add it there. That is marked as visited. Okay, let's do this thing. For all the neighbors I'm traversing, and while traversing, what would I do? I'll try to add it to this one. I'll try to add it to the this visited map or copied map. Copy map, which is already copied, that means so already visited. So what I'll do is copy map okay, I won't do this thing here. Basically, I'll remove this. I'll iterate through, and if copy map is contains key current sorry, contains key neighbor, then continue. If it does not contain, then create a node like copied neighbor is equal to new node, and then add to the map. Copy map dot put neighbor and copied neighbor. So I added, and also this has to be linked to the parent of this one. Current dot so copy map dot get current dot neighbors dot add copied neighbor. But if neighbor is null, okay, if we are instantiating it, then it is creating a new array list. So it cannot be null, so it will be already instantiated. So we can just add it to that neighbor. So always it will go through that, and if it's already created, then we don't have to copy it. Let's see. Okay, node cannot be converted to int. Okay, it's all neighbors are node, right? So neighbor dot val, I guess on data. And it was okay to add me here. I think I removed that one. Copy map current comma. Current, this one is must return a copy of all the nodes in the original graph. Okay. Am I missing the link somewhere here? Node.copied neighbor, creating the new node, and I'm adding it as current node and get current, and the neighbors dot add copied neighbor. So from the copy map, I'm getting the copied version of that one, and then to its neighbors, I'm adding the copied neighbor, its neighbors list, and then I'm putting the copy in the copy map also. I have the neighbor and the copied neighbor. Okay. If copy map contains neighbor, continue. Where have I missed? If it's empty node, then value is equal to 0, and if I just provide value, then it will instantiate to new array list. So visited is a map, hash map. Okay, they are doing the same thing. If visited dot contains key, return visited dot get of node. Clone node clone node is equal to new node of why one needs to pass this one. Don't have clone neighbors as of now, and it's empty array. The key is original node and the value being the clone node. Okay. Did all that. Neighbors dot add. Did the similar things, I guess, in different way. must return a copy of all the nodes in the original graph. Okay, this is a good use case to maybe troubleshoot and copy root value 1 neighbors. There are 2 neighbors. Okay. Edges 1 3 1 3. It's like the same edge there. Duplicate versions, but had we traversed around it, then we would have known more. Can we print it? Let's see. And return else. Val. See, and then okay, I just wrote a simple logic to print it. So now let's call this one. Print traversal node and then new hash set. Let's call it as copied node just to be better, consistent. Okay, it looks like 1 2 3 4 and 1 2 4 is returned. Yeah, 1 2 3 4 and 1 2 4 is returned. Why 3 is missing? That is the big question now. Why is 3 missing? Should we figure out troubleshooting or should we figure out debugging? Okay, let's have this utility method for later. On that. I'll focus here. So we came here. We saw we are iterating through all the neighbors and then seeing if the copy map contains the neighbor, then we don't have to do anything. We'll continue. If not, we are creating the copied neighbor and then adding okay, that is so bad. We are never running the TFS traversal. Traversal of neighbor from, yeah, that's the core of the logic. Once we copied the current neighbor and added the current copy map, okay, and then we need to run the traversal. Something's wrong in this logic. I'm getting confused in this logic. In the DFS traversal, I came here, I'm iterating through each of those nodes, and then once I'm copying the neighbor. Once I copy the neighbor, what should I do? I have a copied neighbor. Then copy map is getting okay. Let's write neat a code. Copied neighbor I have created with the neighbor, and then copied current is equal to let's get this one out the way here. Node copied current is equal to copy map. So that I don't have to do it again and again in each loop. So I'm is equal to copy current. Okay. Now this is copied current dot neighbors dot add copied neighbor. I'm adding it as a copied neighbor, and then in the map I put the neighbor so that I don't have to. So whenever the next time neighbor comes, okay, whenever that neighbor comes next time, it won't be reflected. So now 4 is added as someone else's child, so it won't be added as neighbor of 0 again. That might be what is happening. Yeah. So if 4 is represented, 2 is represented, 3 is there, 4 is there, then it won't be coming again as the children of something. And 1 can never be in anybody's neighbor list, basically, because yeah, 1 is already there. We added it in the copy map and we are checking it. It cannot be copied again. So what the logic should be is, the logic should be, if it is already there, then yeah, then don't continue. If it does not contain key, then copy neighbor would become copied neighbor is equal to this one. Okay. Copy map dot get if it contains the neighbor, then just get that neighbor. Otherwise, just return the existing one. Just create a new one and return it, and then add that copied neighbor here. Wouldn't this run forever? Then should we stop? Yes. Runs forever. How are they handling it? the visited part, I got it a bit mixed up. That's why it's making it difficult. So I already added the quote node here. I'm in a single method there. How it should not, how it doesn't work here. TFS traversal for the node. I'm returning the copied node here. I have the copy already, copied node put into copy map. So once that is done, copied current is copy map dot get of current. Okay. And then I'm iterating through each neighbors of the current, and then copied neighbor will be copy map dot contains neighbor. Okay. Then I'm just returning the copy map get neighbor. Otherwise, I'm creating a new node, and then I'm appending that copied current dot neighbors dot add the copied neighbor. Once I do that, copy map dot put okay copied neighbor. What if I had created this one here? Again, the same thing is happening once it's added as neighbor. Okay, finally. That was exhausting. I didn't time box it. Sorry for that. I need to be more disciplined with my time management. So let's pause this one. Let's take a break. And I'll see. I'll decide if I want to continue today or if I do a new stream tomorrow. I'll start with trees or something.